Welcome, space enthusiasts. Today we're delving deep into one of the universe's most enigmatic and powerful phenomena, supermassive black holes. These colossal entities, with masses millions or even billions of times that of our sun, are not just the stuff of science fiction, they are the hidden engines of cosmic evolution. But what if I told you that these black holes, often seen as mere celestial oddities, might actually hold the key to understanding the very life cycle of galaxies? What if these giants are responsible for starving their galaxies, halting the birth of new stars, and steering the fate of the universe? Let's begin with the basics. Galaxies in the universe are categorized into two major types: those that are actively forming stars, known as star-forming galaxies, and those that have become quiet, producing very few, if any, new stars. Our own Milky Way, for example, is a relatively quiet galaxy, but it wasn't always this way. Scientists have long been puzzled by what causes this dramatic shift in galactic behavior, leading to the cessation of star formation. For decades, astronomers have known that supermassive black holes reside at the centers of most large galaxies. These black holes have the mass of millions, sometimes billions of suns, concentrated into a single, incredibly dense point. While their gravitational pull is immense, the idea that they could somehow influence an entire galaxy, especially one spanning thousands of light years, seemed far-fetched. However, recent research is turning that assumption on its head, suggesting that these cosmic giants might be far more influential than we ever imagined. A groundbreaking study led by Tao Wang of Nanjing University has provided compelling evidence that ties the mass of supermassive black holes directly to the amount of cold gas available within galaxies. This cold gas is crucial because it serves as the raw material for star formation. The researchers found that the more massive the black hole at a galaxy's center, the less cold gas is available for forming new stars. This means that as these black holes grow, they effectively starve their galaxies, halting the birth of new stars and pushing the galaxy towards quiescence. But how exactly do supermassive black holes manage to starve their galaxies? The process isn't as straightforward as one might think. While black holes are known for their intense gravitational pull, this force alone isn't enough to influence an entire galaxy. Instead, it's believed that the key lies in the energy output of these black holes, particularly when they are in an active state, known as an active galactic nucleus, AGN. During this phase, the black hole accretes matter at a rapid rate, releasing tremendous amounts of energy in the form of radiation and high-speed particles. This outflow of energy, often referred to as black hole winds, can have a profound impact on the surrounding galaxy. One of the most fascinating aspects of these black hole winds is their ability to heat and expel the cold gas within a galaxy. This gas, which is necessary for star formation, is either heated to the point where it can no longer collapse to form stars or is ejected from the galaxy entirely. This process is sometimes called AGN feedback, and it plays a crucial role in regulating star formation within galaxies. The more massive the black hole, the more powerful its winds, and the more effectively it can quench star formation. Recent observations have provided direct evidence of this process in action. In some galaxies, astronomers have detected massive outflows of gas, moving at speeds of thousands of kilometers per second, being driven out by the central black hole. These outflows are so powerful that they can strip a galaxy of its star-forming material, effectively ending its ability to produce new stars. What's particularly interesting is that this process doesn't happen in isolation. It can affect entire galaxy clusters, influencing the evolution of multiple galaxies at once. But the influence of supermassive black holes doesn't stop there. Another key aspect of their impact on galaxies is the concept of galaxy starvation. This theory suggests that black holes can prevent galaxies from replenishing their supply of cold gas by heating the surrounding intergalactic medium. The intergalactic medium is the vast reservoir of gas that exists between galaxies, and it's from this reservoir that galaxies draw their star-forming material. When a black hole heats this gas, it becomes less likely to cool and fall into the galaxy, effectively starving the galaxy of the material it needs to form new stars. This starvation process is thought to be particularly important in the most massive galaxies, where the central black holes are also the largest. In these galaxies, the black hole's influence extends far beyond the galaxy itself, affecting the intergalactic medium on a cosmic scale. The result is a gradual decline in star formation, leading to the quiet, quiescent galaxies we observe today. But while the evidence for black hole-driven galaxy starvation is compelling, it's not the whole story. One of the most intriguing findings of recent research is that not all massive black holes are associated with quiescent galaxies. In some cases, galaxies with active black holes continue to form stars at a rapid rate. This has led scientists to propose that there might be other factors at play beyond just the mass and activity of the black hole. One possibility is that the orientation and structure of the galaxy itself could play a role. For example, galaxies with more chaotic or irregular structures might be better able to retain their star-forming material, even in the presence of a powerful black hole. Another possibility is that the timing of the black hole's activity is crucial. If a black hole becomes active after a galaxy has already accumulated a significant amount of cold gas, it might not be able to expel all of it, allowing star formation to continue. Moreover, recent simulations have suggested that the interplay between black holes and their host galaxies is far more complex than previously thought. These simulations indicate that black hole winds might not always lead to the immediate quenching of star formation. Instead, they could trigger a cycle of star formation and quenching, where periods of intense star formation are followed by phases of quiescence, driven by the feedback from the black hole. These findings highlight just how much we still have to learn about the relationship between black holes and galaxy evolution. While we've made significant strides in understanding how black holes can influence their host galaxies, the exact mechanisms and processes involved remain an active area of research. As our observational techniques improve and as new data becomes available, we're likely to uncover even more surprises about the role of black holes in shaping the universe. Looking to the future, one of the most exciting prospects in this field is the potential to observe these processes in real time. With the advent of next-generation telescopes, such as the James Webb Space Telescope, astronomers will be able to study the early stages of galaxy formation and evolution with unprecedented detail. This could provide critical insights into how black holes influence their galaxies from the very beginning, helping to solve some of the remaining mysteries about their role in the cosmos. So, what does all of this mean for our understanding of the universe? In many ways, it forces us to rethink the traditional picture of galaxy evolution. Rather than being passive entities, galaxies are dynamic systems, constantly shaped and reshaped by the forces within and around them. And at the heart of this process are supermassive black holes, acting as both creators and destroyers, driving the cosmic dance that governs the birth and death of stars. As we continue to explore the universe, it's becoming increasingly clear that black holes are not just the monstrous endpoints of stellar evolution. They are fundamental to the very fabric of the cosmos. By studying these enigmatic objects, we are not only learning about the nature of gravity and space-time, but also uncovering the secrets of how galaxies, including our own Milky Way, have evolved over billions of years. In the end, the story of supermassive black holes is a story of extremes: extreme mass, extreme energy, and extreme influence. It's a story that challenges our understanding of the universe and our place within it. And as we look deeper into the cosmos, we're likely to find that these cosmic giants have many more secrets yet to reveal. So keep your eyes on the stars, and remember, sometimes the most powerful forces in the universe are the ones we can't see.